Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at the first section of Chapter 5, having to do with experiments. So I'll scroll on down. Here we are at Chapter 5. We'll open up this PDF file, and here we are. So, last year, we talked about analysis of variance, which was a situation where we had samples from separate populations, and we asked the question, are the means for these populations equal, or alternatively, is there at least one pair that is different? We still are interested in that situation, but now we are going to conduct an experiment. And when we conduct an experiment, we have a single population we're drawing samples from, and then we are going to randomize those observational units into different treatments. And after we impose the treatment on those experimental units, we'll observe a response, and then we want to ask the question, is the mean response for these different treatment groups all equal, or is there at least one pair that's different? So it's the same analysis of variance hypothesis, but the difference is how we're taking those observations. In this case, we are now randomizing observational units to each treatment to observe that response, and that's the experiment. So that's analysis of variance. We know how to do that. So the thing we're going to add right away is blocking. And blocks are used to help us create homogeneous subgroups when there's extraneous variation due to things we can't control. So the experiment I gave in the introduction was, so you can read this example too, but the experiment I gave off the top of my head in the introduction is that, say you are conducting experiments in the morning, in the afternoon, and in the evening, and you're doing something that either has to do with chemistry or biology, where the rates of reactions depend on temperature and maybe on how much light there is for photosynthesis, for example. And in those cases, the morning is different from the afternoon, which is different from the evening. And so the idea here is that is extraneous variation, the time of day. That's not the thing you care about. What you care about is you are imposing different treatments. Say in the morning, maybe you have 3 different types of treatments, and you want to ask, does whatever your response variable is, does that differ between your 3 treatment groups? And so you want to know those differences. So we're going to block on the time of day, so that we're going to reduce the variability from the extraneous variation due to temperature and how much light there is, and that will give us more signal to noise to detect differences between our treatments. Okay, so there's another example here that you can take a look at. We've seen blocking before, even last semester, with paired experiments. So, say we've got 2 treatments that are to be compared, and maybe these are treatments, how about what is the difference, or how about what's the difference in heart rate between someone doing exercise and someone at rest? Okay, so one way to do this experiment without blocking is to just take a bunch of people, make them exercise and measure their heart rate, and then take another separate set of people and let them just sit in a chair for 5 minutes and then take their heart rate. Alternatively, a better way to do that experiment is to have every person have both treatments. So let them sit for 5 minutes, take their heart rate, and then let them exercise, jumping jacks for 2 minutes. That's a long time to do jumping jacks. And then measure their heart rate, and then take the paired difference. So we did that last semester. And that each person is their own block. You know, I'm different from you are, and I have my own resting heart rate and exercise heart rate, and the effect of exercise is the difference between those two values. And that's a nice way to reduce the variability between people, but get at the cleanly at the effect of the difference in exercise treatment. Okay. So that's a case where blocking are people. So there's a history here. A lot of experimental design had to do with agriculture. In fact, Ron Fisher, who designed a lot of the experimental design methodology and statistics, most of his work was in agricultural applications. So we're going to, in this section, look at randomized block experiments with only one factor, where we've got one type of block that controls for extraneous variation, and then within each block we will randomize experimental units to the different treatments. And that is the randomized block design. The motto that goes along with this is block what you can, randomize the rest. So any nuisance variability that can be accounted for by blocking something, by doing everything at the same time or at the same temperature or by the same graduate student taking measurements, right? So if I'm going to do a set of experiments and you're going to do a set of experiments, we both maybe have a slightly different style. I'm conscientious of some things but not others, and same thing for you. And so the person doing the experiment should be a block. So all the experiments that I do is in a block, the experiments you do are in a block, and our advisor, that's a third block perhaps. Okay, so block what you can, and then randomize into the treatment groups, conduct the experiments, and do some analysis. All right, so let's look at an experiment here. This is an experiment I love. It has to do with treatments for itching. So we've got 10 male volunteers between 20 and 30 years old, okay, basically college students, who were used to study as a study group to compare 7 treatments. So we've got 5 drugs, a placebo, and then a treatment which is no drug, to relieve itching. And this is basically torture. So each subject was given a different treatment on 7 study days. The time ordering of the treatments was randomized across days. That means that not everyone, so there were, how many? 10? The 10 volunteers. So for each of the 10 people, they didn't start with the placebo as the first treatment, and then the first drug is the second treatment, and the no drug is the third treatment, and so on. Everyone was randomized in a different order. And that's because there's potentially time-related effects that persist and can affect the outcome of subsequent days. And that's not something we're interested in studying. So by randomizing, we put those sorts of effects into the error or the unexplained variability in the model. Okay, so except on the no drug day, the subjects were given the treatment intravenously, and then itching was induced on their forearms using an effective itch stimulus called cowage. I should have looked this up. I think I remember as a kid having itching powder and thinking that was funny. I'm an adult now. I don't think that's funny anymore. It really itches for a long time. It's awful. But anyway, so these guys are given cowage to make them itch, and the response is, how long did you feel itchy on your forearm? And so then we've got this table. All right, so we've got the rows of the 10 different patients, and then we have the 7 different treatments along the columns. These are not the order that they were given in. Remember, each patient was given these 7 treatments in a random order, but they're just organized in this way. Ideally, this table would also, the full data table for this data would have the order that the drugs were given. Okay, this is sort of a simplified version of that. All right, the full names of the drugs are up here in the text. All right, so to whom does this, what population does this inference can it be made to? As I trip over my words, males between ages of 20 and 30. That's the group of people we sampled. And if it happens to be college students, it's maybe not even all males. It's sort of more affluent males who go to certain, schools and so on, and maybe even within a certain department. All right. So that just means that we can't really extrapolate to children or senior citizens or women. Okay. All right. So we'll read that data in, and here's the table. So let's do the analysis. All right. So we'll start with the model. So we've got 2 subscripts here. So assume that you've got this randomized block experiment. So we've got Y, I, J are the individual observations. I here is for the ith block. And in our data example, each person is a block. Okay, so this is person 9. They're a block because they are self-similar to themselves, and they'll have different reactions to the different treatments. And we want to know the differences between treatments. J here is which treatment it is. So Y, for example, Y, I, J, where I is 9 and J is 2, might be block 9. 2 would be the second treatment. So YIJ for Y92 is 89. Mu ij is the mean for that group plus error. And we're going to break this mu into different components. Here we are. So this mu is going to be the grand mean. That's just mu all by itself. So mu ij is mu plus alpha I. Remember, I has to do with blocks. So alpha I is the effect of who you are, which of the 10 men you are. Okay, some people have really sensitive skin and may itch for a long, long time, and some people are more rugged than that and may not itch for very long at all. And so alpha I is going to account for those differences between people. J is the treatment, so beta J is the effect of the treatment. So if beta here is negative, that means you'll itch less than average, less than mu. And if beta is positive, that means you itch longer. Okay, so ideally we want the treatment that makes beta the smallest, the most negative. All right, so this idea of taking the response and breaking it into, the response here is actually the Y, Yij. Yij is the mean, or the center, plus error. And we're going to decompose that mean in different ways. And in this case, we're decomposing that mean into the grand mean, then an effect due to blocks, and then an effect due to treatments. All right. So here's an analysis of variance table. We're going to start looking at ANOVA tables for block effects and treatment effects when we have more than two treatments or more than 2 blocks, because we'll have degree of tests that are degrees of freedom more than 1. And just like analysis of variance, where we ask, are all the population means equal or not, we're testing, a k-1 degree of freedom test there. and we're going to start looking at this table. And when we reject the hypothesis, say that treatments are different, then we need to go in and look at which pairs differ. Okay, and so that's what this is saying here. So for example, the null hypothesis that we're interested in is on the betas. Is beta 1 equal to up to beta j? Are all the treatments equal? We actually don't really care about the block effect, right? You know, is the amount of itching that Tim experiences different than what John experiences, and is different than what Igor experiences, and so on. We don't really care about that because it doesn't generalize to the population. That we have different people is sort of a nuisance, you know, that we're not all replicants. So we're really just interested in the treatment effect. So we typically, even though this test will show up in the output, we rarely care about whether block is important. What we do care about is that block has absorbed some variability, some of our total variability, so that our error variability is smaller, which allows us to better observe the difference between treatments. Because after all, the sums of squares, the total sums of squares, this bottom line, equals the sum of the block sums of squares, the treatment sums of squares, and the error. So the more we can account for in the block, the less there is in the error, and the better we are able to see the treatment effect. Okay. Get rid of that nuisance variability. Okay, so that's what this paragraph says. We often don't care about block effects. All right, I'll let you read this section, and let's get to the analysis. By the way, just because I skip something doesn't mean it's not important to read. So do spend the 2 minutes and read those. All right, RB is for randomized block, analysis of the itching data. So we started off with data, if I'm paging up here, in wide format. And we need to get this into long format so that we can analyze it. That means right now we've got basically 7 observations per row, and we need to reshape that to have a single observation on each row. So I'll page back down. All right, so the itch data looks just like that table did above, and we'll start by reshaping this by melting it into a long data frame. Now we've got 70 observations, 3 variables, so we've got which patient number it is. So these numbers go 1 to 10 and then 1 to 10 and repeat 7 times. We have each of the treatments there, and then we have the seconds, that itching that these poor boys had to suffer itching. I guess they're men. They're men. All right. So let's just look at the first 3 and last 3 observations, okay? So last 3 observations, patients 8, 9, 10 on the last treatment. All right. We want both the treatment to be a factor, but it's also important for the patients to be factors because the difference between patient 1 and patient 10 is not 9 units, right? They're all basically separate categories, these people. So we need that to be a factor. All right, so let's start by plotting the data. Okay, plot, plot, plot. And there's a lot going on in this plot. I'm sort of unhappy with how busy it looks, but hopefully we can focus on some of the main features. So first thing to do when you're reading a plot is to read the axes. So unless you want to read the title, okay. So along the horizontal axis, we have the 7 treatments. And I've sorted these, basically I put no drug and placebo on the left because I think of those as being control conditions, and the 5 drugs are to the right of that. And they're not in any particular order. On the vertical axis, the response is the duration of itching. Okay, so let's just keep in mind that 300 seconds is 5 minutes. This poor guy was itching for almost 7 minutes or so. That's a long time to feel uncomfortable. Okay. Obviously I don't have any perspective. For example, giving childbirth. All right. So most people on the low end for these will itch about 100 seconds, so almost 2 minutes. The average here, the grand mean, is this dashed line that I've put on top. That's about at 160 seconds, so about maybe 2.5 minutes or so. And then we've got diamonds, which are the means for each of the treatment, for each of the treatments. We have box plots showing the distribution of the 10 men in each condition, and I've also connected the dots for the men. And so those are the blocks. Each man is a block. So this orange line that goes way up and comes down and so on is someone who generally has fairly sensitive skin. They're on the high end of the itching time. And there's some other people, like some of these blue ones, which are on the lower end. And so the blocking here is controlling for the sensitivity between people in their skin. It's not perfect. These lines are not parallel. You know, they're but it basically there are some people with more sensitive skin than others. Okay. So I'm sort of expecting the block to be important just visually here. All right. Maybe the last feature I didn't emphasize is that there are confidence intervals around the diamonds for the 95% confidence intervals for the mean for each group. Placebos tends, yeah, okay. Anyway, so let's scroll on down. All right, so let's fit our linear model. So we have 2 factor variables, and seconds is a continuous response. So we've got seconds by treatment and patient. Patient is the block here. So put in our itch.long data set, and we'll start off by looking at the analysis of variance table. And here we're specifying type 3 errors, or type 3 sums of squares, and I will explain those at another time later. So right now we'll just accept that type 3 is what we want. I can explain it now. So type 3 means what is the contribution of patient sums of squares, for example, after accounting for treatment already being in the model. Okay, so it's basically the sort of the standard parameter estimate table that we look at when we look at these p-values. We're asking, after controlling for everything else, is this one still important? Okay, in this case, patient is important, at least at a 0.05 level, and treatment, this is asking, does treatment explain variability after controlling for patients? And this also says yes, at least at a 0.05 level. Other types of sums of squares are type 1 is probably the most popular after type 3, which is called sequential sums of squares. That means you start with the intercept, so you sort of account for the grand mean, and then you add treatment, but this p-value will just be, is treatment important after the grand mean? So this does not control for patients, which is the next one. So that's why it's called sequential. And then the next sums of squares will be patient after controlling for everything before it, and so on. Typically, the order that these variables go in is not in a particular order, and so sequential sums of squares or type 1 sums of squares is not important for us. So we will always use type 3 because we are interested in the effect of one factor conditional on everything else being in the model, regardless of the order from top to bottom that they are in the model. Okay, so here we found that patients describe quite a big proportion of the sums of squares. That's really great. Otherwise, that would have gone into the residual sums of squares, and we would have had a lot of variability there in our error term. So let's take a look at our summary, and this is where heads are going to start popping. So here's the parameter estimate table and all of the coefficients. So let's start by going to the very bottom, looking at the F statistic. Let me get rid of this. I'm sorry that that thing pops up. Look at the F statistic. This is on 15 degrees of freedom, and this says that jointly, patient and treatment seem to explain the length of itching better than only the grand mean. Great. So after looking at that, we would then actually jump up to the ANOVA table, step 2, and ask, is it treatment or is it patient or both that are important? In this case, we find that they are both important, conditional on the other being in the model. And the third step is we would scroll down to the individual coefficients. And these coefficients, we're going to become experts at interpreting these at the very end of the chapter, but I will point out right now what's going on. So the intercept plays a very important role. It describes the mean number of seconds itching for the baseline group for both the treatment and the block. So notice that there were 7 treatments, but there's only 6 rows for treatment. Also, there were 10 patients, but notice there is no patient 1. It starts at patient 2 and goes through patient 10. That's because, so remember what the baseline was for treatment. That was the no drug and patient 1. So intercept is, so 188 seconds is how long patient 1 itched using no drug. Okay? That's the baseline group. Everything else is relative to that baseline. So all of these effects right here have to do with, so 13 says that patient 1 itched 13 seconds longer on the placebo than they did on no drug. On the PAP-V, patient 1 itched 72 seconds shorter than the baseline, no drug. So basically 188 plus 13, basically 202 seconds is patient 1 on the placebo. 188 minus 72 is 116, roughly, seconds is how long patient 1 itched on the PAP-V treatment. Okay. Next, patient 2, 35. This is relative to the baseline. The baseline, the intercept group, is no drug, patient 1. So when we look at this number, 35, this is the difference between patient 1 in the intercept and patient 2 on no drug. So patient 2 on no drug is 188 plus 35. I'm no good at doing this in my head, I'll be honest with you. 123 seconds. Okay? Now what gets interesting is when you ask, how long did patient 2 itch when they were on the placebo? So you've got to add both to the baseline, right? So you start at patient 1 on the no drug, you move to the placebo in terms of treatment, and then you move to patient 2 for the patients. So you have 188 plus 13 plus 35. Do it in your own head. And that's how long the patient 2 is predicted to itch on the placebo. Add those 3 numbers together. Let's see, 188 and 13 is 188 plus, I'm rounding up, plus 35. All right. 237 is what we expect patient 2 on the placebo, how long we expect him to itch. Okay. All of these hypothesis tests are all only relative to the baseline group. So almost all of these tests are not interesting to us. Do we care about patient 1 being different on the baseline no drug versus the placebo? Probably not. We want to know overall how treatments compare over all the patients. So these are not the comparisons we want to make, says Obi-Wan. So we will soon come back and make these tests that we care about. But it is important to note that these are not what we care about. All right. I am sure I described all those things. All right. Multiple comparisons. Let me page down for a moment and all right, let's do it. Multiple comparisons. So these are the comparisons we want to make. So there's a package called MultComp, which does this general linear hypothesis test. And there's another package which we're going to use a little bit later, which does this also, called LS-means. And when you use the generalized linear hypothesis test function in the MultComp package, we want to do multiple comparisons and correct those multiple comparisons in some way. For example, you can do Tukey contrast corrections, or you can do Bonferroni or Fisher's, which doesn't do any multiple comparison correction. And so in this function, we take the regression, or the linear model object. We need to wrap it in analysis of variance, AOV. And then we need to specify the linear functions that we're comparing. So we're doing MCP, that's multiple comparison, over the different treatments, right? So treatment was one of our variables. We also have patient, but we don't care about differences between patients, only between treatments. And we're going to control comparisons over treatments using Tukey's test. Okay, so there's a lot going on in this one function. We'll drop that into the general linear hypothesis test, just this object I called itch.t. The dot .t is standing, this is just conventions that I use for myself. That's for the treatment. All right, so when we look at this summary, I'll scroll down. It says simultaneous tests for general linear hypotheses. We're doing Tukey contrasts for means. This is the linear model object we cared about. And the linear hypotheses that we're testing are differences between all pairs of treatments. And so I'm going to scroll down a bit just to show you all the comparisons, right? So there's seven different treatments, and so there's 7 choose 2 different comparisons being made. So is there a difference between the mean number of seconds itching under the placebo versus no drug? The difference here is 13 seconds. It's positive. That means placebo minus no drug. Placebo was the longer itching. So you did worse under the placebo than no drug. Okay, that happens. Is that different? So here's the estimate, 13. Here's the standard error, 24. How do we get the t-statistic? We take the estimate divided by the standard error, so that's about a half. And that is not very extreme. And so we have a large p-value. And these p-values are already upward adjusted based on the Tukey comparisons. So then we can work down all the way through all of these comparisons and see what happened. So PAP-V versus no drug, fairly big estimate, but still pretty big standard error. T-statistic of almost -3, which is a big t-statistic, but after controlling for all of our comparisons that we're making, a p-value that's almost 0.07. Okay, there is one big difference here between PAP-V and the placebo. 86, so that's over a minute, almost a minute and a half. And that's really the only big one in here. And just to remind you down here, the significance codes, so the star that we observe here is 0.1, is the 0.016 is the p-value, and so that's here. So that means the p-value was somewhere between 0.01, and 0.05. So that's how you read this table. We also had a dot up there that was between 0.1 and 0.05. And everything else that has a blank, here's the blank, bigger than 0.1. All right. So you can also do Bonferroni, just showing you an example. You can do that right within summary. Give it the general linear hypothesis test, specify that you want the test to be adjusted using Bonferroni, and you get all those comparisons as well. And this one, the only one that stands out is that one. Bonferroni is very conservative, makes those p-values very large. You can see they're all, many of them are hitting 1. Another thing you can do here is, with the general linear model object, is you can plot it. So here's the summary of the general linear model object with Bonferroni corrections. And if we create that plot, the rest of the stuff that's here is basically just making margins a certain size. I'll zoom out a little bit. And here are the means, are the dots between placebo versus no drug, for example, and then the confidence interval for the difference in means. And there's only one here, PAP-V minus placebo, where the confidence interval does not include the vertical line at 0. All right, so we'll come back in the next video and look at doing diagnostic analysis here. But basically, the thing that we've learned, if we go back to the plotted data after seeing what the difference is, so PAP-V seems to be the winner. If we page way up to our data, that's what we see. We see PAP-V and the placebo. That's the biggest difference vertically here. A lot of these other treatments visually do basically better than no drug or the placebo, but statistically we don't have enough evidence to say that they're different. We have evidence to say PAP-V is better than the placebo, and some marginal evidence to say that it's better than no drug. But everything else seems, at least statistically, to be roughly equal. All right.